Good morning, everyone. My name is Chuck Geisler. I'm the Director of Sales and Marketing with American Engineering Testing, and would like to thank you for joining us today for the first in a series of webinars that AET will be providing here in 2022. We still have a few folks joining us, so I'll take care of a couple of housekeeping items to get us started. So today's webinar is going to be able to provide 1 hour of professional development hours. All of the attendees today will be receiving a certificate via email for today's presentation so that you can apply those towards your continuing education credits. As we go along today, we ask that you put any questions that you might have in the chat box, and we will answer as many of those questions as possible at the end of today's presentation. And if we're unable to get to some of the questions, Chris will be providing an email at the end of his presentation, or you can reach out to him via LinkedIn, and we will follow up with you directly with that. So today's speaker is Chris Broughton. He is a professional geologist and also a certified professional geologist. And he's a senior petrographer here at American Engineering Testing and is a graduate of the University of Minnesota. And he has been with us for 16 years, and he's held various positions as a field technician, bridge inspector, and aggregate laboratory coordinator. And he's been in our petrography department for the last 10 years and became a senior petrographer in 2018. And today he is going to talk about forensic geology petrography, what aggregate analyses tells us about concrete. And Chris has significant experience in this and has performed analyses on aggregates from 49 U.S. states and 18 different countries and territories. So with that, Chris, I will turn it over to you and we'll follow up here at the very end. So thank you again for joining us today.
All right, thanks, Chuck. We'll get this started right now. And Chuck, can you just confirm you can see my slide?
Yes, I can. We're good.
All right. Well, here we go. This is want to thank you guys all for attending today, and it's exciting to start this thing off in 2022. So it's a nice day to start something off inside, because I think in Minnesota here we're at about -2 or -3 degrees. I'd rather be giving this presentation inside than doing field work. I apologize to anybody doing fieldwork in our climate right now, but let's get started. So I'd like to start this off with what exactly forensic geology petrography is. So the first few slides here, I am gonna generally read off the slides, but I do have some pretty cool photos later that I'll just be talking about. But starting off, petrography is a geologic term applied to the microscopic analysis of rock. The science can also be applied to concrete and other cementitious materials. So forensic geology is using those geologic principles to look for reasons why a material structure is exhibiting problems. Some of the standards we typically follow in our department from the American Society for Testing and Materials, ASTM. ASTM C294 is the descriptive nomenclature of concrete aggregates, and C295 is the actual procedure on how to perform the petrographic analysis on concrete aggregates. ASTM C1721, it's basically petrography on dimension stone. ASTM D4992, do petrography on riprap or erosion control stone. And ASTM C856/C457, that is petrographic analysis of concrete. I'm not going to touch too much on the concrete subject or the riprap or dimension stone. I'm going to kind of focus more on aggregates, but I'll touch a little on concrete. So why would some people use petrography in the construction industry? Well, Construction aggregate quarries and gravel pits use it to determine if they have or how much potentially deleterious meaning problem-causing substances exist in their sources. The same can be applied to dimension stone, veneers, pavers, and then again, riprap, erosion control. We also use it for troubleshooting hardened concrete and masonry problems. Masonry, we actually have a procedure for that too. That's ASTM C1324, I believe. And that one's kind of fun because we get really old masonry from historic buildings. You know, I think we've had 200-year-old masonry in our lab. And we can run some petrography and some chemical analysis on it to tell what type of mortar it was. So when they're doing rehab of those historic buildings, they can try and match the mortar as best they can. So it looks seamless. And then, like I said, condition surveys and then rehab of structures, quality control of the construction materials, and then research and development. So going back to petrographic examination on concrete aggregates using ASTM C294/C295, some of the examples of potentially deleterious substances in aggregates are shale, coal, chert, soft iron oxides. Those can cause pop-outs and staining. Now, I'll go back to shale quick. Shale is one of probably our biggest offenders in the Midwest area in our natural gravels. And I'll show you some pictures later of what can happen. Chert, chert is one rock, don't get me wrong, but there's two different types of chert. Like one is chert, which is really hard, dense. You know, you break it apart and it can kind of splinter. It has a conchoidal fracture, just like you would expect quartz. Other chert is hydrous chert or tripollitic chert. And that has kind of, for lack of a better term, kind of weathered and it's become softer. It turns like a bright white color. You can pick it out in natural gravels really easy. And those can cause pop-outs. So the good, hard, dense chert, those won't cause pop-outs, but that softer hydrous chert can. Other things we look for in thin section might be like quartz, microcrystalline, cryptocrystalline. Cryptocrystalline meaning you can't see it with a microscope. Microcrystalline meaning you can't see it with your eye, but you can find it as in a microscope. And then strained quartz, and we'll talk about those later. Other forms of quartz or silica would be opal, chalcedony. Chalcedony is the quartz, like a fibrous radiating quartz that you can find in chert, and I have a cool picture of that later. Volcanic glass, tritomite, and cristobalite, which are high temp forms of silica and volcanic rocks. I've never personally seen tritomite and or cristobalite, so hopefully someday we'll be able to see those. Other things, micaceous minerals, they can increase the water demand, and create a pore bond in the cementitious paste. Pyrite and pyrrhotite can produce staining accompanied by volume increase. And then the mineral gypsum can create internal sulfate attack. So those are some of the minerals and rock types that we look for that can cause problems in concrete. There's more, but we only have so much time. So why do we put so much time and effort into petrography and quality control for our aggregates for construction? Well, aggregate fine and coarse combo is approximately 70% of what concrete is made of. Different concretes, have different additions, but general rule of thumb is 70% of your concrete that you see is a coarse aggregate and a fine aggregate combination. So this just shows for crushed stone, like this is quarried and crushed rock. In 2019, 1.53 billion tons of crushed stone valued at $18 billion was produced. And I thought this was interesting. In 2020, this is the height of shutdowns and the pandemic and all that stuff, and it didn't really drop that much for crushed stone. 1.46 billion tons produced, and $17 billion made off of that. And of the most common crushed stone we see is crushed carbonate rock. Limestone and dolomite combined for about 70% of the crushed stone used. 15% granite, 6% trap rock or basalt, 5% miscellaneous stone. Then you got sandstone and quartzite coming in the last place there. So in the sand and gravel industry, kind of the same thing, except it didn't go down too much. 2019, 970 million tons for valued at $9 billion. And then in 2020, somehow they produced less, 10 million tons less, but they made, $0.2 billion more, which is pretty nice economics to work out for those guys. Leading states, I like to put this in here: California, Texas, Arizona, Minnesota, Michigan. Minnesota, my home state, we're usually in the top 5 for natural gravel, sand and gravel producers. We have really nice sand and gravel deposits in the metro. One problem we're having, though, is, with urban sprawl, more of those nice natural sand and gravel deposits are being built on top of, or different cities, if they're not being built on top of, don't want to allow permitting for those to be mined. So it's a battle that producers will have to face here, but other people have to face it too, because resources are dwindling and construction keeps going up. So they have to figure that out. So when I start on an ASTM C295, a client, an aggregate producer, will send a bucket of rock in, usually a 5-gallon pail, probably around 50 pounds of rock. You have a gradation run on it per ASTM C136. And once you get that gradation done, you split the sieve sizes, you save all the sieve sizes separately. And then I kind of dig through the rock and I find different colors, different textures, anything that separates one rock from another, and do my best to pick out enough rocks that will help me, generalize the sample as best I can. So you can see here this thin section, or this picture to the left. I've picked my rocks out. This is a natural gravel from Arizona. I picked my rocks out and we've made thin sections. So, also I'll address that is a cup of coffee. I've done this presentation before and people have asked if it's beer. It is not. It's coffee. I know it's a fancy glass, but we're geologists. We get our fingers dirty pretty much every day. I figure it's okay to let yourself feel refined once in a while and drink coffee out of a fancy glass, maybe with your pinky up. I don't know. So we make thin sections. I identify all these lithologies, and some of these lithologies are most likely the same. Like I bet 5 of those rocks were all extrusive felsic volcanic rocks. So you can kind of group them together. They just might have different colors, which makes the hand sample pick a little bit more difficult. So this pink one here, that's probably an extrusive volcanic. This one is an extrusive felsic volcanic. So you have different colors, different variations that you have to pay attention to. So it's nice, once you look at all the thin sections, you identify your lithologies, then you go back and you separate, you go back to your separated sieve sizes and you pick out 150 particles. You split out 150 particles per sieve size, and you kind of try and identify each particle as best you can, looking for any soft particles, looking for any other potentially deleterious particles, and then calling it out in your report later. So if you have a pile of rocks, a natural gravel, this is what you're looking at. And like I said, you can have with a natural gravel, you can have up to, 15 thin sections because there might be 15 different looking lithologies in there. But once you start getting more experienced at it, it gets a little bit easier to do picks. If you follow my laser pointer, pick, that's a granite. Over here, you can probably find there's a granite right there. And then you can start looking like, okay, so these granites, they're nice, they're angular, they're nice clean fractures, they look crystalline, they look hard, they look solid. You can qualify those as, a good, hard, solid aggregate. Over here, you can kind of see this particle. It's a little rounded, a little dull, a little earthy. You're going to want to double check that particle. I'm going to take that and I'm going to scratch it and see how soft it might be. We use a weighted brass pencil. I think it provides 2 newtons of force. So it's supposed to take out, if there's strength differences between the person performing the test, right? So you have one person that might be really, really strong and can dig a Mohs hardness of 3 right through that, or and not be able, and right through that thing. And you might have somebody who's not as strong, might not be able to scratch it because they can't put enough force on it. So it takes that part out of it. So we'll use that weighted pencil, and we'll get it and see if it can provide a deep scratch, and then we'll qualify that as a soft particle. And you just kind of keep going through that, and then you create a spreadsheet later and identify like percentages of shale, percentages of granite. So your client will know your percentages of lithologies they have and potential bad ones. On the flip side, if we get a quarried and crushed aggregate like this is from a granite quarry, you might only make 5 or 6 thin sections because there's not much variation. You see there's maybe 3 or 4 or 5 different colors, different textures in there. 3 or 4 of those are probably going to qualify and fall under the granite category. Then I can see some over here. There's some fine grained stuff, black. It's probably basalt or a diabase dike that was in the granite quarry. And then you do the same thing, make the thin sections, do the rock descriptions, identify your lithologies, and then separate it out. So here's an example of why we let producers know what kind of deleterious particles they have in their aggregate sources. So this is actually a photo of these 2 photos with the bottle cap are photos of my concrete driveway, my old driveway, I should say. And I caught this pop out. I came home from grocery shopping and I stepped out of my vehicle and I caught this pop out happening in action, which was pretty awesome. So I took a photo right away. Bottle cap was the only thing I had for scale. And I uncovered the mortar flaking. That's concrete mortar flaking. I picked it off, and that's a nice big shale particle that we have up here. That's probably, close to a 1/2 inch, 3/4 inch diameter. And those things produce a lot of force, and shale is very, very absorptive. If you are not familiar with shale particles from the Midwest, you can take a shale particle and you can stick it right to your tongue. And it's so absorptive, your tongue will kind of suck into it, and you have to rip it off. I actually, as a geologist, if there's any other geologists on here, we've all licked rocks, and I actually did that in front of a group of people of about 80 people when I was giving a presentation on this a couple years ago, and I was thinking about how funny that would be now, licking a rock in the time of COVID. They'd probably ban geologists from rock outcrops. So this is another photo of what shale pop-outs can do. This is a garage slab, obviously taken a while ago. I think my manager took this, and each circle I think is a shale pop, and they are allowed a certain number of shale pops or pop outs in general in concrete. I think, maybe a couple pop outs per 30 square feet of concrete or something like that. I've only seen the spec once, but we're there to identify how many particles of shale are in there, and then hopefully it doesn't happen to the concrete producers, and or they don't get any complaints from customers for how many pops they have. So I wanted to show this as another example of why we might do C295s on quarries. This is actually a quarried basalt from Washington State, the West Coast, and got these thin sections, dug through the sample, started seeing all these nice angular crushed crystalline basalt particles, got them in thin section, beautiful thin section of the basalt, nice plagioclase crystals. Well, as I was digging further into the sample, I started finding all these like same color, dark black particles, but they're all rounded edges, dull, earthy looking, and they were soft. So we made a thin section of that, and this is what it was. It's basically like a mud rock with some detrital silt grains in there. So I called our client, who was a laboratory manager for a testing firm out in Washington State, and I said, you know what, this is very weird. I'm seeing all these shale particles or mudstone particles in this crushed basalt. And he said, that's interesting because they had been getting higher than expected results for physical testing of the aggregate. So we talked a little bit. He actually decided to send one of his guys out into the quarry, and they took a picture of this, which you got nice solid basalt up top, nice solid basalt on the bottom. And that, I believe he said, was about a 2-foot thick seam of shale mudstone. And basically, I haven't seen that in my neck of the woods, so it was different, but their geologist kind of explained this as somewhat normal out there. It's a process of abduction. So think of it as taking a knife blade and the sharp edge of the knife, pointing your opposite hand finger down, pointing the knife blade to your fingernail, and then pushing your fingernail straight down like a subducting plate. All those fingernail scrapings that are coming up and being left on top of your sharp knife blade, that's basically what happened. This subducting plate had the top scraped off by the overlying plate. And so those are ocean floor basalts and ocean floor sediments that just got scraped up and kind of mixed up together. Kind of cool thing. But like I said, that kind of answers his question on our petrography, our lithologic identification, kind of answers their question of why they're seeing higher than normal results. Like a good quality hard basalt will give you really good physical test results. And when they're a little bit higher, somebody who knows what they're doing and looking at those results and seeing those numbers, you can kind of say, well, something's not right. Either our equipment's off, our procedure's off, or the rock is off. So just gives you some things to double check. We also do petrography on lightweight aggregate. I've only done this maybe 2 or 3 times in my career, so it doesn't happen that often, but I like to show it because lightweight aggregate is pretty cool engineering. So this is expanded shale, and they can make it expanded shale, expanded clay, expanded slate aggregate. There's also natural lightweight aggregates like pumice, perlite. So this expanded shale particle, they actually heat it to 1,000 degrees, and then the gases generated, expand the material, make it pop up like that, like popcorn. And excuse me, it has a glassy texture. So the way you do petrography on something like this is you can separate it based on shape, surface texture. Sometimes they develop a skin. You can kind of see this, what they're talking about here, like a little skin where it doesn't seem like it had too much of those gases generated on the outside. So surface texture, vesicularity, or finding incompletely expanded particles. Most of the time I've documented pyrite minerals in there too, that they can be concerned about. I'll show a really nice picture of why to be concerned about pyrite in a little bit. And I've showed this picture once before in a presentation, and a question was asked, well, if lightweight aggregate is glassy, can it produce alkali silica reactivity? And I found a good explanation of yes, it can, but the glass phase of expanded clays, shales, and slates may be alkali reactive, but expansion of concrete from this has not been observed because any siliceous gels that are generated are accommodated within the abundant air-filled cavities that characterize the expanded particles. So basically, the siliceous gels that might be produced are kind of trapped in these air bubbles. And if you're not sure what I'm talking about for alkali silica reactivity, I will get into that a little bit later. Got some cool photos. We also do ASTM C295 petrographic analysis on fine aggregate or sand. And you can see this picture on the left is a natural sand. This is Minnesota sand. You can see it's mostly subangular to subrounded. Our sand is really good in several pits and locations. You can pretty much pull out natural sand and have it meet, once you scrape off the gravel, that is, you can meet C33 concrete aggregate specifications for fine aggregate. The other side is manufactured sand. So this is crushed and quarried rock. This right here is actually a syenite. So what the producer will do, they can use some of their waste rock or fines or whatever, and they can make a nice concrete sand. One thing to be aware of with manufactured sand is that the angularity of it can increase water demand in your concrete mixes. And people use manufactured sand for different reasons. I think I was in a quarry tour in North Carolina, and they use manufactured sand just because they don't have any real good natural sand around that meets concrete aggregate specifications. So they have to use manufactured sand. And on our side in Minnesota, I mean, our natural gravel and sand deposits, a typical one is about 20 to 30% gravel. So you're looking at 70 to 80% of that deposit being sand. You can't sell all that sand. So all that really nice sand that can be used for concrete in other areas of the country, obviously shipping rates will take that out, but that gets put back in and used as really good fill for when they start to do reclamation of the pit. This is the thin section picture of the number 200 sieve. So like coarse aggregate, on fine aggregate, we also run a gradation. We take the gradation and we do a hand sample count, lithological count on the number 4 sieve and the number 8 sieve, because we can see those pretty good under our stereo zoom microscopes. Anything below that, number 16 sieve, 30, 50, 100, 200, and the pan, we make epoxy plugs. So we put it in a little boat and we fill it with epoxy, let that harden up, and then we can put it on a thin section slide and make a nice slide. And for fine aggregate, we just have to do like a point count. So we're not doing rock descriptions or anything like that. We're just going through and identifying a lithology and saying granite 1, basalt 1, quartz 1. So lithologies and mineralogies. And by the time you get down to the finer sieves, like you can see here, it ends up being pretty much all minerals and no lithologies remaining. Got the red arrows are pointing out some strained quartz grains. You got some plagioclase feldspar in here. You got some micas. This might be a zircon or something, but you just go through and you identify those minerals and you identify anything that can potentially be harmful to your concrete, just like you would in a coarse aggregate. And this is an example, just like I showed that pop out of the shale particle in my driveway. This is a shale particle in that's fine aggregate, and you can see 1 millimeter scale bar. So this is probably about 1 millimeter wide. It would probably pass a number 16 sieve. Excuse me. And or number 8 sieve. And we'd probably end up getting this in thin section and calling it out and then giving a percentage. But this is why we do call it out and make our clients aware. I mean, this little 1 millimeter particle, it started to create alkali silica gel here, green arrow, filling an air void that was in the concrete. This is another shale particle over here. It's starting to crack up, starting to do the same thing. But these shale particles, these tiny little guys, started to crack up the concrete. Now, these sand fine aggregate shale particles aren't going to really do much damage to your concrete at depth. But if they are near the surface of your concrete, they can start to cause those pop-outs. They can start to cause pop-outs because of freeze thaw, because they're so absorptive. They can also cause chemical pop-outs, which is ASR induced pop-outs. And that is actually called near surface alkali silica reactivity. And I'm going to touch on that in a little bit. But it's pretty cool that, I mean, it's not cool for ready mix producer. Don't get me wrong. I don't want this to happen to our concrete and have people have to tear it out and start over again. But just being able to see this stuff, it is pretty cool to know what kind of action this can actually have, like the combination of alkalis in the concrete, silica in the shale, creating this gel. And I'm going to get into alkali silica reactivity again in a little bit here and get more in depth in case you don't know what that is yet. All right, here's another good one. This is a concrete paver, and our client wanted to know what caused that iron stain. And you can see that right in the center, that black, that's the actual particle that's remaining. And that particle is a sand particle. It's probably about 2 millimeters. So that's right around a number 8 sieve. And being that small, look at the the volume of the stain it produced. You know, that's a large noticeable stain, which is why it was sent to us. I think it was placed at somebody's home, and the owner, you know, noticed that ugly stain, so they had them send it back, and they came and replaced it, and they sent it to us and wanted to know why. So we did a saw cut right through it, see if we can try and save some of that particle. And we have run into this before. It ended up being a pyrite particle, and it's a kind of an interesting pyrite particle because it's not just straight up pyrite. It's pyrite made of like millions of little tiny pyrites. And so the client sent their quality control people into their pit, and they started looking for these dark particles. We just said they'd probably be dark particles. They started collecting these dark particles and separated them before they went into their mix, and they sent them to us. So we got to look at them, and this is what the pyrite concretions look like under 10x magnification. So they did find some pyrite ones. Now, looking at them, they don't look like pyrite, but the closer you zoom in, this over here to the right, 50x, you can start to see the brassy color start to stick out. and you can start to tell, like, okay, yeah, that's pyrite. Well, we got a new toy this year, and or last year, 2021, and excuse me. We got a scanning electron microscope, and we were able to zoom in. This picture here is 850x. So this red circle, that is one little framboidal pyrite particle. And it's cool, perfectly spherical little particle. And this, we actually got lucky and caught one in cross section. And you can see how many little tiny pyrite minerals that's actually made up of. Again, moving over here to the last image, this is 1700x. This SEM is really cool. These pictures are awesome. But you can see that cross section way better. You can look at how many little tiny crystals that thing's made up of. So imagine the surface area that's available there for that to react. Those pyrite, that picture, that previous picture of the stain here, this was probably only in service for a few months before that stain was that pop out happened and that stain was created, because of all that surface area being exposed to atmospheric conditions and starting to weather. And we even got some other cool geology stuff. You can see some of the euhedral pyrite crystals, some pyramids. In this other picture over here at 850x, you can see some dye pyramids. So that SEM is really fun. But great example. And this is called framboidal pyrite. If you're not familiar, it's that's after a French word for raspberry, la framboise. My wife would kill me for murdering that French pronunciation because she majored in French and she lived in France for a while. So good thing she's not listening. All right, another iron sulfide mineral is pyrrhotite. Pyrrhotite is big right now. It's very hot topic. It reacts faster than pyrite, and it can cause expansion, leading to cracking into the concrete. You can see this is some of the weathered pyrrhotite here, and it's starting to corrode and basically expand and cause cracking that leads into the concrete. This is a better visual. It actually started to create radial cracking around the single aggregate particle. Now, this is more of a big deal right now on the East Coast of the United States and up in Canada. I believe they might have even had problems first up in Quebec. And then in America, it was Connecticut where that really started to experience these problems with pyrrhotite. They had all these housing foundations made out of concrete, and they started to crack and kind of fall apart. They did several studies on it, and they concluded that it was this pyrrhotite mineral. And they actually did enough background research to figure out that the pyrrhotite belonged to this one aggregate produced at one quarry. And I'm not saying anything that isn't public information right now, but yeah, they traced it back to one quarry, and I believe it was a metamorphic rock, a gneiss particle, or a gneiss lithology, and it had a lot of pyrrhotite in there, and it created this path of destruction, I guess, out there. So much so that like the USGS has created a general map of pyrrhotite locations to make people aware of where pyrrhotite might be. Now, it's a very generalized map, and some people just, you don't have to worry about it. Like our Minnesota gravels, we don't have to really worry about pyrrhotite. I don't see pyrrhotite in our gravels. So, you know, it's based on country, but or on geographic location, but it's there regardless to examine and see if you might have pyrrhotite in your area. The other thing that's going on right now is, and I don't know if this happened yet, but last I saw in 2021, there was a petition for the adoption of a bill in Massachusetts about how to deal with pyrrhotite and how quarries and aggregate producers have to look for and test for pyrrhotite. So it's a big deal out there. A lot of insurance agencies we're getting on board. We got quite a few concrete cores from insurance agencies trying to see if it really was pyrrhotite or something else. Because I think they might have put money, the state might have put money towards helping people pay for repairs if they could prove that it was pyrrhotite. But very interesting nonetheless. Sucks to be those homeowners. I get it, but as a geologist and a concrete petrographer, it's interesting stuff. All right, so this next slide is fine aggregate. This is a manufactured sand, and it was a crushed granite. So one thing I noticed here when going across is all these micaceous minerals. Those are all muscovite. All the green arrows are muscovite minerals. And so per ASTM C294, because micaceous materials have a high surface area, they can influence the properties of freshly mixed and hardened concrete. Aggregates with a high mica content can reduce workability and increase the water demand of the concrete. The shape and perfect cleavage of micaceous minerals may result in a poor bond to the cementitious paste. So it's another mineral. I mean, it's rare that I've seen too high of a mica content. And to be honest, I've only seen one specification that said you have to be under a certain percentage of mica. But we point it out nonetheless and make people aware, our clients aware, that this could potentially be an issue, or if they're not aware of it. So it's interesting what kind of role geology plays in it's all natural materials, so you have to the good comes with the bad sometimes. That granite aggregate is typically a good aggregate to use, and manufactured sand, if you have a high mica content in your granite quarry and you decide to make a sand, you can start to crush and alleviate those micaceous minerals and separate them out, and it could cause problems in the sand. Probably won't be an issue in the coarse aggregate. All right, now we're on to alkali reactive textures, alkali aggregate reactive textures. And this first one is an image of an alkali carbonate reactive texture, also known as ACR. So this texture is what a petrographer would look for in thin section to call out potentially reactive for alkali carbonate reactivity. You see a really fine-grained micritic calcite matrix. Probably has some insoluble residue in there, like clays or quartz minerals. And then you'll have these euhedral dolomite rhombohedrons, basically looking like they're floating in the calcite matrix. So that's a texture that we look for. And this is per the Federal Highway Administration. Alkali carbonate reaction was first observed in Kingston, Ontario, Canada. And I've never seen rock from there, but they were the first ones to see it. And alkali carbonate reaction isn't as well understood as alkali silica reaction. But the typical carbonate aggregate that's associated with the alkali carbonate reaction is an impure dolomitic limestone. So to be classified as a dolomitic limestone, you're looking at, in the mineralogy of it, 10 to 50% should be dolomite. And then the remainder would be calcite. So that makes it a dolomitic limestone. So the expansion produced, if it's used as aggregate in concrete, the alkalis in the cement will react with the dolomite. And the expansion produced can occur within the aggregate particle, The dolomite crystals in the aggregate are chemically altered by the alkali solutions from the concrete and causes de-dolomitization. Brucite is a magnesium hydroxide mineral that is usually formed during destructive ACR and typically evident in expanded concrete. So it's one piece of evidence that you would look for in concrete if you have ACR. But just looking at the aggregate itself, this is the texture that you're looking for. All known, this is kind of an interesting little fact, I think is kind of crazy, but all known reactive carbonate rocks are from the geologic time period known as the Ordovician period. So basically there's been a few areas of the United States that have experienced like ACR. I've actually never personally seen it in concrete, but I've seen these textures. And typically when I see these textures, I see these textures mostly in these seams. So this all in the middle here, the light gray is limestone. And then these darker seams are filled. If you look over to the right, this is a thin section image of one of those seams. And you can start to see that it's got that micritic calcite. It's got the euhydrodolomite rhombs. It's got some other insoluble residue up here. Some of these minerals are probably quartz. Kind of interesting though. I've only seen this dolomitic texture personally in my career in these seams, and I've seen these seams here in probably from 5 or 6 different samples, and I don't know the locations of them. We weren't privy to that. Sometimes we get rock and aggregate sources to look at, and we don't get a geographic location or project names or an area. So we're kind of stuck just looking at it. I do like kind of knowing a general idea, because then I can at least look up Bedrock geologic map and kind of helps my rock descriptions and conclusions a bit, but we work with what we get. So, but it is kind of interesting. So now on to alkali silica reactive textures. You can see here so alkali silica reactivity is more well known, ASR, and this here is a great picture that I took. Pat myself on the back, sorry. But those red arrows pointing to really, really pretty chalcedonic quartz. You can see the fibrous nature of it. And then the rest of it is crypto to microcrystalline quartz. This is a chert particle. And these forms of silica are, potentially reactive, and one would say like known reactors. On the flip side, the more common potentially reactive alkali silica reactive texture we see is strained quartz. That could be in a slightly metamorphosed granite or gneisses. You could see it in sandstones from detrital grains that have some sand grains in there that came from maybe a slightly metamorphosed rock body in the past. But strained quartz, basically, you're looking at undulose extinction. So normal quartz or unit quartz will basically, when you're under thin section, will blink. And it'll blink between white and black, whatever to be general for colors. But if you look at these strained quartz particles here, it's more of like a wavy extinction. That's what undulatory or wavy extinction, that's how we identify strained quartz. And strained quartz is called out as a potential reactor. The other cool thing to note here is this plagioclase crystal with this deformation twinning, showing that it indeed was, somewhat metamorphosed rock. I like calling out cool stuff when I see it, not just necessarily what's good or bad in the rock. But the way alkali silica reactivity works is the alkalis in the concrete react with these quartz minerals. And if moisture is present, it can create a gel. And this is what that gel can look like and what bad ASR can look like in your concrete. If you notice all this white deposit, that's the alkali silica gel, the precipitate of the reaction extruding or exuding from the wall. And it started to crack up because of the expansive forces start to crack up that concrete. And it can just, if there's enough of those reactors around, if there's enough quartz, if there's enough water, if there's enough alkalis, it can keep going. Now, the gel is amorphous. It can take upwards of 20 years or more to develop, so you might not even see this for a while. And then the chemistry of the gel can be either a sodium or a potassium silicate, depends on the type of cement that's used, but can be pretty destructive. Another picture here, this is of a dam. You can see if, obviously you have concrete, you probably have some kind of silica-rich aggregate in there, and you have obviously a water source because it's a dam. You can get ASR and it can be destructive. Dams are definitely high on the list of alkali silica reactive structures that you have to be aware of. And I've seen a presentation where they actually have pretty bad ASR, but what they do is their concrete has expanded, their structure has expanded and quote unquote grown. So they'll actually cut sections of concrete out, and then they'll put like some steel beams in to take some of the load, and then they'll just wait for it to expand more, and then eventually coming to a point where they're going to have to replace it. But it's pretty interesting. And actually, I saw a presentation put on by the U.S. Army Corps of Engineers where they had a dam, I think it was in Tennessee, that they had alkali carbonate reactivity, and they said their dam grew 14 inches. I don't remember how many years that took, but it's pretty crazy. They actually saw cut and relieved the pressure of expansion and to increase the life, I guess, for a little while. I'm sure it's going to be on their list of replacements here shortly. All right, so this is near surface alkali silica reactivity. I touched on that earlier. You can see here, this particle is the offending particle. This is Arizona gravel. This is an extrusive felsic volcanic rock. So like a rhyolite, or it could be even like a tuff, like an ash rock. So when it's highly reactive. We also say, I should mention that we say in petrography, when I'm doing the initial C295 analysis, I say potential alkali silica reactivity, because it might not. You might see the textures, but it might not ever react. It might not might have used a lower alkali cement, or just might not be moisture around to create the reaction. But this one had the constituents within the rock. And then what happens here is if you have these ASR textures, the reactive rocks, aggregates, and you put a coating system on top, you can see here, I believe this was a pickleball court. Those coatings can trap moisture. And even though this is Arizona and people don't think of it being very moist down there, there's enough water vapor moving through the soil and up from the soil through the concrete. And then that water will be trapped by that impervious barrier that they put down for the coating. And it'll sit there and it'll give enough moisture to start that reaction to happen. So like I show here, that started in this particle, started to crack up. And then if you look over, or you can follow the alkali silica gel with the green arrows up to where it's caused a pop out in that pickleball court. Over to the right, you can see a magnified view of that, how this started to crack up really bad. And obviously when it starts to crack up, it'll expand and cause cracking. And then you can see the gel kind of following those cracks. Pretty cool stuff. Again, I know I always say I have to catch myself sometimes saying things are cool when really it's costing people money to replace. But those flooring issues and coating issues, they have to be aware of potential alkali silica reactive rocks in that concrete before they put the coatings down, because it can trap that moisture unless maybe they put a vapor barrier in new construction. But then that can cause other problems with your concrete that I won't get into in this presentation. But so this is just another cool picture of alkali silica gel. You can see most of the time it's white. When it starts to dry out, it'll start to crack. It's almost like mud, start to crack like mud cracks. It's called desiccation. Gel over here, it's filling a void, and you can see it can also be clear. This is what alkali silica reactivity, what the gel looks like in thin section. This thin section to the right, to the left, is from the same sample as I just showed. These were glass beads that were used as a decorative aggregate in the side of a pool. Well, glass beads are made of amorphous silica, and like I mentioned, volcanic glass is on the reactivity index. So, and that's amorphous silica. So glass beads are the same thing and can be highly reactive, especially when you're near a water source like a pool. The whole side of this thing just started falling apart and crumbling off, but made for some, again, some cool pictures. That alkali silicon gel, you can see it starting in the glass beads and cracking it up and then kind of going into the paste and into the next one. On the right side image, you can see this was like a metamorphic aggregate particle, probably like a gneiss or a metagranite. And again, that gel started in the aggregate particle and started to follow the cracks and start to crack up the concrete and cause bad stuff to happen. Now, there are ways. This is ASTM C1778, a really good standard if you're not familiar with it. I don't know how long it's been out. I don't think it's been out much more than 10 years, but I could be wrong on that. So this kind of gives you an idea. I don't want to be all doom and gloom with ASR because it's certainly not like that. You can do evaluations of your aggregate source to get an idea. So like this flow chart says, you start with the field history or testing history. If it's a new source or if you're doing exploratory stuff, you perform a petrographic analysis of the rock, and we'll tell you if it has those reactive ingredients, either ACR or ASR reactive. So sticking with the ASR, you perform a ASTM C1260 test, which it's known as the quick and dirty kind of alkali silica reactivity test. You basically crush your rock down, your aggregate, and you make a mortar bar, and then you place it in sodium hydroxide, and then you measure the expansion as it goes. And I think it takes like 3 weeks to start and finish that test, which is pretty fast. And it's also known as like a harsh test, so it can give some, test results that maybe your aggregate says it's reactive, but it's really not in the field. But if you fail this one, you would move to the C1293. Now, this one is definitely known as the more accurate test. However, it's 1 year long. So a lot of, a year in the construction industry is a lifetime. So many things change. But I think once you get started on a yearly rolling system, that first year, yeah, you're going to be waiting a long time for results, but then as soon as you get that result, it's good for a year. So then you have time to submit your next one right away. And next thing you know, you'll just be current. One problem with that is if you add any, well, I'll get into that in a second, but if you pass this one or fail this one, if you pass it, then you're good. If you fail it, then you would move on to other measures. And those other measures might be to add supplementary cementitious materials. This to the left is a photo of slag cement. Slag is a byproduct of the steel manufacturing, and it creates these glassy shards. They are supplemented for some of the cement used in the concrete, and that can help mitigate alkali silica reactivity. Now, different aggregates need different percentages, so you have to do some further testing and experimentation, but it can be maybe 10 to 15% or upwards of 30 to 40% addition to help mitigate that reactivity. On the right side, that's fly ash. All these are little spherical glassy particles produced from their byproducts of coal burning. And with coal plants, being put offline more and more, the resources for fly ash are dwindling. So that's causing a concern for some of our ready mix suppliers in the Midwest, because they like using fly ash not only to mitigate for ASR, but they use it for other physical things for concrete too, like controlling heat of hydration and different things. But so these are some options to help curb and mitigate ASR. And then lastly here, this is another table from C1778. I really like that. So this actually has a rating system for ASR. Like it has classes, class SC1, some deterioration from ASR may be tolerated, and like non-load bearing elements, or not exposed to moisture, or temporary structures. You don't have to really worry about ACR or ASR. On down here on class SC4, ASR cannot be tolerated. Major bridges, power plants, dams we touched on, nuclear facilities. Obviously, some of these should be pretty common sense, that you have to take several precautions in construction of those. But interesting that they actually called out and made a table for that. All right, I think that concludes my presentation. So thanks for attending. If you have questions that we don't get to today, you can email me here. You can follow me on LinkedIn. I try and post things every Monday under the hashtag Petrography Monday for something I might be working on. And I'll leave that up and turn it back over to Chuck.
Thanks, Chris. Interesting presentation, and lots of ways that poor aggregates can negatively impact concrete, for sure. I don't see that we have any questions in the chat. Oh, here's one from Adrian. Have you considered the use of automated mineralogy, TestScan or QEMS scan in aggregate characterization?
We have not considered using it. I don't think we've talked about that with my other colleagues. So I'd have to do some research on that and see what that is all about. Okay, I see some other questions here. Should I just read them, Chuck?
Yeah, sure. Go ahead.
All right. Do you ever perform any kind of radiometric dating on the aggregate rock samples you collect as part of your research? No, we do not. That's just not something that we need to do, and we don't need to charge our clients for that extra testing. I don't know that if a client really wanted to, we could send it somewhere, but we don't do that in our laboratory. And then looks like there's a follow-up question from Adrian. Does the use of fly ash in aggregate have toxicity concerns? No, not that I'm aware of. It's used in concrete, so to clarify, but so when used in concrete, it kind of gets bound up and locked in that concrete. So it shouldn't cause any concerns when the structure is demolished, and that concrete is typically reused as recycled aggregate. So as far as I know, I don't think there's any toxicity concerns that I'm aware of. What if efflorescence occurs? Could you be more specific? We do see efflorescence quite a bit in concrete for various reasons. Sometimes it's a concern for the deleterious nature of what can happen to your structure. Sometimes it can be dealt with and just left alone.
Okay, Chris, it looks like that's the end of the questions, and we're about 5 minutes. Well, maybe one or two more here, and then we'll wrap up.
Okay, I got 3 questions here. Ryan, Adrian, and Court. So we'll get to all 3 of these. Is efflorescence and ASR similar? No. Efflorescence is typically crystalline growth from crystalline precipitate growth on concrete surfaces or inside concrete. And ASR is that specific reactivity, and it creates an amorphous gel. So I would say that they are somewhat similar because they're a chemical reaction creating a precipitate, but different in the nature and type of precipitate created. And then water percolating through cinder block, can the precipitate have toxicity? I would imagine you're referring back to the fly ash. Again, I'm not aware of anything. I haven't looked at any studies or seen any studies that say that the water percolating through the concrete can pick up toxicity from fly ash. So I'm not sure if I can answer that. And then is quartzite more susceptible given its metamorphic strain nature? Yes, quartzite definitely is alkali silica reactive because it has a bunch of strained quartz in it. And the Sioux quartzite, it's a really nice pink quartzite formation located down in like South Dakota and southwestern Minnesota. That is known to produce alkali silica reactivity in concrete. However, it can be mitigated with those fly ash or what other SCMs, and it's a really good, hard, durable concrete aggregate when used correctly. So, all right, I guess that wraps it up. Thank you everybody for attending, and join us for the next one.
Okay, thanks, Chris. Thank you for everybody joining, and we'll follow up here with the PDH certificates. Thank you again. Take care.